We were discussing about specific heats, and here when we were talking about specific heats or any of these formulas for changes in internal energy, enthalpy, or entropy, we need to remember that the relations we came up with in the last class apply only when we are dealing with a single phase. Okay, when we are dealing with a phase change, the specific heats are not even defined, and when we're dealing with when we are dealing for phase changes, we need to rely on the the Clapeyron equation to obtain the changes in enthalpy HFG, or the change in the entropy SFG, or and then we can basically use HFG to determine UFG as well. Okay, simply from the relation between HFG and UFG, right? U is equal to H plus PV. So it's important to know where these relations apply, and all the relations that we discussed only apply for a single phase. Now, even when we are talking about a single phase, right, we have been dealing with the values for specific heats, which are only dependent on temperature, right? So till now we have been talking about variable and constant specific heats, where these values, the Cp or Cv, these are only functions of temperature. Okay, so if you look at chapter 9, we were considering the gas to be behaving like an ideal gas, and for an ideal gas, the specific heats are only dependent on temperature. So the value that you took for Cp 1.005 from table A20, these are all values where we were talking about cases that either represent ideal gas or at low pressure case, right? So these specific heats, which are listed in table A20, which we used frequently in chapter 9, are called zero pressure specific heats and are denoted by Cp0 and Cv0, simply because these are valid at low pressures. Okay, at low pressures, Cp depends only on temperature. But when you go to higher pressures, and I'm not talking 1 bar, 2 bar here, I'm talking about maybe 70 bar, 100 bar, right? When you go to high pressures, the specific heat the specific heat values depend on both pressure and temperature. It is not a function of temperature alone, and therefore we need to figure out how to take that into consideration. How can we evaluate CPs at higher pressures, CVs at higher pressures? And the way we could do that is simply by coming up with another expression, and that's what we did in the last class. We basically started with this expression for entropy and then apply the test of exactness to end up with these two equations. And here we said we'll integrate the Cp part here because it relates to it has the dP component right here, and you have to sort of integrate equation 16 from zero pressure to the pressure that you want, and this is the formula that's going to end up giving you the CPs at any pressure and temperature, right? Here the Cp value is something that you can obtain from table A20, or it's a value that you can also derive using some formulations. So this is how you get the Cp values at higher pressure and temperature. Now the question is, how do we get Cv values, right? How can we get Cv right here? Now, if you want to get Cv, if you could also write a similar integral for from this equation, or from another equation where you're integrating over certain pressures, or a simpler way could be you could find a relation between Cp and Cv, right? You could find something that Cp minus Cv is equal to something, right? And that's what we're going to do now. Okay, so we're going to develop a relation between Cp and Cv, simply because it can be first of all, it can be used in such cases where you have an expression for Cp in terms of pressures and temperatures. And once you evaluate Cp from this complicated integral, which may be complicated, not always, you'll be able to come up with the value of Cv simply by another relation. Okay. The other situation where this makes sense is where you just want to go ahead and measure Cp or Cv experimentally, and you want to use this relation to come up or calculate the value for the other specific heat. Now, the reason we want to do that is because experiments tend to be costly, and we would want to minimize the cost as much as possible. So the question is, how can we come up with a relation between Cp and Cv? Okay. Now, the way we come up with the relationship between Cp and Cv is just the same way we came up with thermodynamic relations throughout this chapter, right? We'll have to look at some differentials and then equate things here and there, and develop another relation which relates another equation basically, which relates maybe Cp minus Cv to something. Okay, so the way we're going to do that is basically by again starting from this the two equations for ds. Okay, we're going to take these two equations. These are the two ds relations relating ds to Cv by T dt and ds to Cp by T dt and so on. So we're going to make use of these. We're going to equate the two, and we're going to solve for dt. So let's see what happens. Let's equate the two. Okay, this is ds on both sides, so they obviously are equal. So here you just take the two things, Cv by T dt plus dou P by dou T dV is equal to Cp by T dt minus dou V by dou T dP. Okay, this is simply equating. Now we want to actually solve for dt. All right, and there's a very specific reason why we are solving for dt. As we go through the derivation, it'll become more clear to us. Now, if you want to solve for dt, I want to take everything, all the coefficients for dt on one side. So let me send this here, and let me send this expression on the left-hand side. Okay, so I'm sending Cv to the right. So what I get as Cp minus Cv by T times dt is equal to dP by dt dV plus dou V by dou T dP. Okay, this is what I have. Obviously, I'm solving for dt, so I can sort of write it, and I can send the coefficient of dt on the right side, and I'll have something like temperature times dou P by dou T dV divided by Cp minus Cv plus temperature times dou V by dou T times dP divided by Cp minus Cv. Okay, so this is one expression where we have dt is equal to some coefficient times dV plus another coefficient times dP. Okay, so this is all what we have here. So now, since temperature, pressure, and specific volume are the three things that you can easily measure, let us assume that temperature is a function of specific volume and pressure. Basically, what we're saying is, if you know the specific volume and pressure at a given state, you should be able to define the temperature of that state. You should be able to determine the temperature of that state, which again is perfectly fine from the point of view of the way we define a state, right? From the state postulate. If you know the two independent intensive properties, we should be able to find all other properties, right? Define the state and all of the properties. And since we're dealing with single phase, pressure and specific volume are certainly independent intensive properties. They also remain independent and intensive during phase change as well, but certainly outside the phase change process, they certainly are independent intensive properties. So if we say temperature is a function of specific volume and pressure, then we can write differential of temperature dt, the total differential that is, as dou T by dou V times dV plus dou T by dou P times dP. Now, the reason I've done all this is because I want you to compare the coefficients of these equations. Okay, if you look at equation 1 and equation 2 right here, both of these are dt is equal to some coefficient times dV plus another coefficient times dP, which basically means that I can equate the coefficients of dV and dP, meaning this term right here, which I've circled, should be equal to dou T by dou V, and this term right here, temperature times dou V by dou T times by Cp minus Cv, should be equal to dou T by dou P. Okay, this is all what I have. Now I can equate any one of these, right? Either this one on the left hand side or the one on the right hand side. I'm going to get exactly the same answer. Okay, and we'll see what that answer is. And because that answer is something that's going to give us a relation of Cp minus Cv in terms of some other quantities and partial differentials. So let me erase this and show you the written part. So this is what we said we did. You want to solve for dt, and then t is a function of specific volume and pressure. You write these two, and then you're comparing these two coefficients. Okay, and no matter what coefficient you compare and take, ultimately we are trying to get Cp minus Cv. Both of them give you the same relation for Cp minus Cv, which is equal to temperature times dou V by dou T at constant pressure times dou P by dou T at constant specific volume. Okay, so this is the first relation for the Cp minus C. This is the first Cp minus Cv relation. Now you can determine the difference between Cp and Cv, provided you know the pressure volume temperature relation for that particular substance. So for example, for an ideal gas, we know PV is equal to RT. So using this PV is equal to RT formula, I could just plug it in here and calculate the partial differential of specific volume with respect to temperature, right? By simply taking V is equal to RT by P and differentiating with respect to temperature. And also I could take the same equation right here and write P is equal to RT by V and differentiate P with respect to temperature again here. And ultimately what I'm going to get is I'm going to get Cp minus Cv is equal to R. Okay, so if you just do it here, for example, Cp minus Cv is temperature times dou V by dou T, right? So this is V. If you differentiate this thing with respect to temperature, you're just going to get R by P. Okay, times dP by dou P by dou T. So this is pressure from the ideal gas equation. If I differentiate this thing with respect to temperature again, I'm going to get R by V. Okay, so this is PV and this is RT. Cancels out to get 1. You get Cp minus Cv is equal to R. Okay, so for an ideal gas, we see that it goes down. The difference between Cp and Cv comes down to R. But this is a very general form, right? This is a general form where for other gases, or for ideal gas for a gas not behaving like an ideal gas, where you have maybe some other relation. Maybe you have P is equal to ZRT, Z being the compressibility factor that you got in Me2O3, or maybe you have some other relation, right? PV is equal to not PV, P times P is equal to R times T plus B by V minus A, or V times A, something like that, right? There are several different formulations that represents the PVT relationship between gas, or even between different fluids, right? Some are complicated, some are easy. The easiest one is the ideal gas equation. But the bottom line here is that once you have this expression, just by using the PVT relation, you should be able to get the Cp minus Cv difference. Okay, any questions? Okay, all clear, hopefully. All right, so here we have Cp minus Cv as temperature times dou V by dou T, right? Partial differential of specific volume with respect to temperature times partial differential of pressure with respect to temperature. Now, this is one way of determining Cp minus Cv, but depending on what information is given to you, you may want to look at other expressions, and that's exactly what we want to do here. We want to sort of eliminate this part here, right? We don't like dP by dt, dou P by dou T, simply because it's not related to any property that we can measure directly. So we would want to actually remove this from this expression. Now, the way to do that is by simply using the cyclic relation. So if you have pressure, volume, and temperature as the 3 variables, you can certainly use the cyclic relation and write in this formula that dou P by dou T times dou T by dou V times dou V by dou P is equal to -1. We already showed it for the ideal gas, right? Now, how is it useful? Well, I have here dou P by dou T, which I want to eliminate, and I can write it in terms of dou V by dou T. I mean, I'm sending this to the other side, send these two to the other side. I can write that in terms of dou V by dou T, change of volume with respect to temperature, times change of pressure with respect to volume. Okay, and this expression, this formula is something that we already had before. So when we substitute this into the Cp minus Cv relation that we just saw, we're going to get Cp minus Cv is equal to minus temperature times dou V by dou T squared, right? This squared of this thing times dou P by dou V. Okay, this is another expression that we have here. And the difference between this and the previous expression is that here we're just looking at how specific volume changes with temperature, and in this case, right, volume changes with temperature at constant pressure. And here we're looking at how specific volume changes with pressure at a constant temperature. I mean, certainly this expression is the inverse of that, but essentially that's what you're looking at. So fix the pressure, play around with the temperature, see what happens to specific volume. You should be able to get this expression. And fix temperature, play with the pressure, and see what happens to the specific volume, and you get the second expression, right? These are again quantities which are rather easy to measure. As a simple example, consider water. Okay, at room, if you are heating water, the pressure is of course constant. It's atmospheric pressure, unless you put a lid on top of the container where you're heating water. Okay, if you don't put a lid, it's atmospheric pressure. You heat it up, and you can easily see when you change the temperature of the water, of course, which increases as you as you heat it up. You can see how does the specific volume change, right? We know that it's going to increase, but the question is how much does it increase? Okay, so that gives you the first part right here. The second part would be keep a temperature constant, right, and pressurize it, the substance that you're looking at. So you could pressurize some gas, you could pressurize water, some other fluid, and then see how much does the specific volume change as you pressurize the substance while keeping temperature constant. Okay, so these two things are rather easy to measure. So this is another expression where we could actually go ahead, measure these two things instead of sort of evaluating them from the relations, measure them directly and evaluate what the value of Cp minus Cv would be at a certain temperature and pressure. Okay, so this is another expression. And the reason we want to come up with this expression is because we want to have several ways in which we can evaluate Cp minus Cv. Okay, we just want to have multiple options. Now, the other advantage with this expression right here is that these terms right here, which represents the change of specific volume with respect to temperature and the change of specific volume with respect to pressure, are measured for a lot of other applications and are thermodynamic properties called the volume expansivity, which is specifically given by this definition. It's beta is 1 by V times dou V by dou T at constant P, meaning it's going to look at the normalized change in specific volume with respect to temperature, right? So whatever is the change in specific volume with respect to temperature, you divide it by the average of the specific volume between the temperature range. Okay, so let's say you take air it's at certain T1 and V1, let's say 300 K, and its specific volume is, let's say, 1 meter cube per kilogram. You heat it up to 302 Kelvin. The specific volume goes up by 0.01, so it's 1.01 meter cube per kilogram. So here, when you want to evaluate beta is going to be 1 by specific volume average times the change, right? So 0.01 divided by 2. Sorry. So the specific volume average that you have here, the V that we have here is specific volume average, and the V average, it's simply 1.005 meter cube per kilogram. Okay, so it's sort of, you're going to look at the change in specific volume for sure, but you're also going to normalize it with the specific volume at the temperature range that you're looking at. Now this is very useful because we don't want to simply look at the change in specific volume. We also want to look at where exactly are we talking about the change, right? How much is the specific volume when we are talking about the changes? So we want to look at the relative change. So this is the first part where we look at change in specific volume with respect to temperature. Okay, and this is extremely important. I'll talk about some applications in a bit. The other part is called as the isothermal compressibility, which is looking at how the specific volume would change when you keep on increasing the pressure at a constant temperature. Okay, now you can notice that there's a negative sign on top before here, and there's a reason for that. Now, if you think about air, for example, fix the temperature constant. Okay, if you keep increasing the pressure, if you keep pressurizing it, we know from experience that the specific volume is going to decrease. I mean, it's going to become more dense, right? So this ratio dou V by dou P, right? The change in specific volume with respect to change in pressure, this ratio is going to be negative because as you increase pressure, the specific volume goes down. So as dP is positive, the top is negative. So this value is negative. But we already have a negative sign on ahead of this here. So this means that the kappa value is always going to be positive. Okay, so kappa, which is the isothermal compressibility, it's always going to be positive. But of course, it depends on how positive, how much is the value, right? If it's small, then the change in specific volume would be small as you keep on increasing the pressure. Whereas for a large value of kappa, same change in pressure will cause a huge change in specific volume. Okay, so this is all what it is about. Now, where do we make use of these properties? Well, we make use of these properties in deciding the material that you want to select for a certain application. As a simple example, let's consider the railway tracks. Okay, so we know that the temperature is going to change throughout the year, especially in Saudi Arabia. There are huge changes in temperature between summer and winter in certain locations. It can go as high as 50 degrees Celsius in summer and as low as maybe -2, -3 degrees Celsius in winter. So that's a 50 degrees Celsius change. And certainly with that change, you're going to have change in the specific volume. Okay, so we know the specific volume is going to change. We know that the railway tracks are going to expand and contract during summer and winter, so we need to leave some space for that. Okay, and some space is always left, but we don't want the space to be very large, right? Because that can put strain on the robustness of the track. I mean, if the gap is too large, if you need leave a too large a gap, then well, you can of course they can get out of pace and create an accident. So you absolutely do not want that. You want, yes, you want to allow for the expansion, but at the same time you want this gap to be small. So you select a substance whose beta value is small, right? So that yes, we know the temperature changes are going to happen, and we accept the fact that specific volume is going to change, but at the same time we are looking for things with very small changes in specific volume. Okay, so with very small changes in specific volume, you can keep the tracks close to each other, and yes, they're going to expand and they're going to contract, but they will still be fine. They'll not put any stress on each other, and they'll continue to operate efficiently. Okay, and that's how we came up with using the stainless steel or the steel for the steel alloys for the railway tracks, right? So you select a material based on its properties, based on your application, based on how you want to deal with it. Okay, so this is one application. I'm also going to visually show you how the change in beta corresponds to change in specific volumes in a bit. But before that, I just want to complete this slide by talking about what happens when we plug in beta and kappa into this equation 19. Okay, when we plug them in, of course, there's no specific volume in here, so we have to multiply with specific volume. When we plug them in, or when we want to include the beta and kappa into the equation, what we get is we need to also multiply with specific volume, and the negative sign goes away because it's taken care of by kappa right here. And we get Cp minus Cv is equal to specific volume times temperature times beta square by kappa. This is what's called as a Mayer relation, and this is another relation, or the third. Now, if you want to count, this is the third relation that gives us the difference between Cp and Cv for a certain substance, right? Again, here, if you know the value of beta and kappa at a certain pressure and temperature, then you can easily determine the value of Cp minus Cv. Okay, so this is these are the three different ways in which you can determine Cp minus Cv. Any questions? Are you guys here?
Yes, yes.
Okay, good.
Yes, Dr. Here.
Okay, things then are clear, hopefully. I mean, I'm not expecting you to come up with these derivations in your exam, but you may be asked the physical interpretation of what's happening here, or you know what these quantities are and how they make sense. Okay, so make sure you understand this, and if there's anything that's not so clear, please go ahead and stop me and ask. Okay. All right, now let's look at this graphic right here to get a better feel for beta, right? How things change with beta. So here in case A, which is the figure on the top, what we're doing is we have initially, let's say air within the cylinder at 20 degrees Celsius and 100 kilopascal pressure. We're having 1 kilogram of air, let's say. Okay. um, and we heat it up, right? And the temperature increases by 1 degree Celsius. We keeping the pressure constant, of course. So this is why you have a piston cylinder assembly. And of course, it's a closed system, so the mass remains same. Now, as you heat it up, we know that the specific volume is going to increase. Okay, so the increase in specific volume is what's shown in this shaded pink color here. Now, let's say you have another substance, another gas, let's say gas B, with a smaller value of beta. Okay, now if you do the same thing, started with 20 degrees Celsius, 100 kilopascal pressure, same mass. When you heat it up by 1 degree Celsius, you will notice a change for sure. Specific volume will increase, but the change in specific volume is too small. Okay, as you can see, this change, this pink color, pink box here, is much smaller than the pink box in case A. So you can see visually that yes, when we increase temperature, of course, specific volume is going to increase at the fixed pressure. But the question is how much is going to increase, and the answer to that is it depends on what gas you're dealing with, right? So for some gases, some fluids, the change is very large. For some gases and other fluids, the change is very small. So this property, which is called beta, the volume expansivity or the coefficient of volumetric expansion, this is again something that's used to identify certain materials, right? Used to identify materials for applications. So now having looked at this visual representation, let's go back to Mayer relation, which gives us Cp minus Cv in terms of beta, kappa, and specific volume and temperature. Let's look at this expression and try to understand something more about Cp minus Cv. Okay. Now specifically, let's look at the right-hand side here. Now we know that the specific volume is either positive or zero, right? It's always going to be greater than or equal to zero. It cannot be negative. Temperature is in absolute Kelvin, so this also can either be greater than or equal to zero. Now we have beta squared, so it's anyway greater than or equal to zero. It cannot be negative. It's a squared thing, right? Whatever is the beta, we're going to square it. Kappa, on the other hand, which is defined as minus 1 by specific volume, dou V by dou P at constant temperature, isothermal compressibility. We already discussed that this is always going to be positive or zero, simply because every time you pressurize a substance at a constant temperature, its specific volume is surely going to decrease, and you already have this negative sign in here before. So this basically means that the overall value of isothermal compressibility is always going to be positive. So when we look at all the things on the right, what we realize is the term on the right is either going to be, the product, specific volume, temperature, beta squared by kappa. It's always going to be either positive or it's going to be great. It's going to be greater than or equal to zero. It's never going to be negative. And since the term on the right is always going to be greater than or equal to zero, this tells you that Cp is always going to be greater than or equal to Cv. Okay, there are only certain situations where Cp will be equal to Cv, but for most parts, Cp is going to be greater than Cv. Okay, Cp will never be less than Cv. Okay, that will never happen because this thing on the right can never be negative. So that's the first thing to remember. Okay, Cp is always going to be greater than or sometimes equal to Cv. Now let's look at cases where Cp will be equal to Cv. Now there are two cases. Obviously, one case would be when temperature is zero Kelvin, right? If you reach absolute zero temperatures, then yes, the difference between Cp and Cv will be zero for all substances. Okay. Now it's not so easy to reach absolute temperature of 0 Kelvin. We can approach it but not reach it. We're talking about really low temperatures, right? We're talking about minus 273.15 degrees Celsius. So no one has ever reached that temperature. So this is, let's say, a theoretical thing. Yes, at this temperature it's going to be zero. No one reaches there. So let's think about a more practical situation where Cp would be equal to Cv. Now, when we're dealing with any incompressible substance, right, such as solids or liquids, where the specific volume is going to remain constant irrespective of how much change you do in pressure or temperature. Okay, for all such substances, when I say constant, it's not going to remain exactly the same. The change in specific volume is going to be very small as you make huge changes in pressure and temperature. Okay, so for all such cases where specific volume is going to remain constant, where the value of beta and kappa are almost going to be equal to 0. For all such cases, again, Cp will be equal to Cv. Okay, and or let's say Cp will be about almost equal to Cv. Now the thing is, for all such cases where beta and kappa are both almost equal to 0, you can cancel out kappa and 1 beta because they'll have very similar values, and you'll be left with specific volume temperature times beta. And this value of beta is very small, right? Maybe 10 power minus 3, 10 power minus 4, depending on the liquid or the solid that you're looking at. And therefore, it brings everything else down to near 0, or Cp minus Cv would be maybe 0.001 or 0.01. Either case, it's almost 0, right? Cp will almost be equal to Cv. So the other more practical situation where Cp is equal to Cv or Cp is almost equal to Cv is when we're dealing with solids and liquids. Okay. All right.